All right, this is section 5.4, so it's chapter 5, section 4, logarithmic functions, and I'm super excited that we're doing this. It's one of my favorite topics in math. We are we have been dealing in one-to-one functions, and one-to-one functions have an inverse function that is defined implicitly by the equation y equals f, or x equals f of y. In particular, the exponential function y equals f of x equals a to the x, where a is greater than 0, not equal to 1, is one-to-one, and has an inverse function that is defined implicitly by the equation y, or x equals a to the y. The inverse function is so important. The inverse of our exponential function is so important that it has its own section in this textbook. It's called the logarithmic function. Okay, so you guys definitely have to write this down. Y equals log with a subscript a of x, if and only if x is equal to a is our base, y is our exponent, and x is our answer. The domain is x values greater than 0. So y is the logarithm to the base a of x. So the little a tells you the base, x tells you your answer, and y is your exponent. So if y equals log base 3 of x, then x equals 3 as our base to the y. So let's see how this works out. If we have 4 equals log base 3 of 81, so we shuffle this around. 3 is our base, 4 is our exponent, and 81 is our answer. So the exponent goes out by itself. This is your base, and 81 is your answer. So if I have y equals log base 5 of x, then we can rewrite this as, let's look at our example problem. We have log base 5 of 1/5, and that's equal to -1. So I write that as 5 to the -1 equals 1/5. All right, so that's converting. We're going to use those properties to change exponential statements to logarithmic statements, and logarithmic statements to exponential statements. So we have these 3 exponential statements. Remember that we're going to rewrite these in log form. So where I see my base, it's going to go in the spot here. Where I see my answer here, it's going to go right next to my log, and then my exponent is going to go on the outside. So this is equal to 3, so here's the exponent, equals log of base 1.2 m. Okay, so let's look at b. E to the b equals 9. So that means my exponent b is equal to log base e of 9. And a to the 4 equals 24. That's 4, my exponent, equals log base a of 24. So now we're going to go backwards and change from logarithmic back to exponent. So here's my exponent. A is my base, so this is a to the 5th equals 4. So a to the 5th equals 4. This one, b, is going to be e to the -3 equals b. And my last one is going to be 3 to the c power equals 5. All right, so now let's evaluate these guys. This takes a little bit of tricky manipulation. We're going to do it by hand first. Then we're going to, your calculator can only handle a couple different types of logarithms. So we're going to look at evaluating, and then we'll bring the calculator into it. So if I want to find the exact value of log base 3 of 81, I go 3 to the what is 81. 3 raised to what power gives us 81? Oh, well, that's 4. So 3 to the y equals 81, and that is 3 to the 4th. So A equals 4. All right, let's look at B. Log base 2 of 1/8. So my base is 2. We're going to raise it to some power, and it's going to equal 1/8. Well, I know if I have a fraction, then my exponent has to be negative. So I look at 2 to the what equals 1/8. Well, I know 8 is 2 to the 3rd power, and since it is in the denominator, I know that means I have a negative exponent of 3. So log base 2 of 1/8 is equal to negative 3. All right, now we're going to look at the domain of a logarithmic function, and I am a definite visual learner, so usually when I look at logarithmic functions, I graph them, but that only works when we have either base 10 or base e. The domain of a logarithmic function is equal to the range of the exponential function, which is from 0 to infinity. And the range of a logarithmic function is equal to the domain of the exponential function, which is all real numbers, negative infinity to infinity. So domain is from 0 to infinity, range is negative infinity to infinity. So what this does is, when we are looking for domain and range, normally we would say, oh, if I have a square root, what makes my square root negative? If I have a denominator, what makes my denominator 0? We're going to add in, if I have a logarithmic function, my domain has to be greater than 0. You can't input anything less than 0 into a logarithmic function. All right. So let's writing that in interval notation. The domain for y equals log base a of x is between 0 and infinity, and the range is from negative infinity to infinity and beyond. All right, find the domain of each logarithmic function. So I have log base 3 of x minus 2. I need x minus 2 to be greater than 0. So because I can only input numbers greater than 0 into a logarithmic function. So x minus 2 greater than 0, which means x has to be greater than 2, or the interval from 2 to infinity. Let's look at B. So I have the log base 2 of x plus 3 over x minus 1. And x plus 3 over x minus 1 has to be greater than 0. So we go, well, the numerator, so when we solve that out, it's x plus 3 has to be greater than 0, and we cannot equal 1. Any value that is in between negative 3 and 1 will make this value less than 0, so those numbers are excluded. So the domain is from negative infinity to negative 3, and from 1 to infinity. And these are both not included because it's not greater than or equal to, it is greater than. All right, so last but not least, C. We have log base 2 of absolute value x minus 1. Since the absolute value function is never negative, the domain would consist of all real numbers except where x minus 1 equals 0. So it's from negative infinity to 1 and from 1 to infinity. All right, let's graph these things. This will be fun. So remember, the logarithm is an inverse of the exponential function, so it's going to be reflected across the line y equals x. So if my exponential function has a point of -1, comma 1 over a, then if I switch these guys, x and y, that coordinate is on my graph. So that 1 over a comma -1 is the inverse. So we switch these x's and y. All right. Oh, so for when a is between 0 and 1, it looks like this. And for when a is greater than 1, it looks like this. So if I have base 2, y equals 2 to the x, looks like that. And log base 2 of x is its mirror image across the line y equals x. Same with y equals 1/3 to the x. Log base 1/3 x is its inverse. So just make note. You can create a log function by making a table out of y equals 1/3 to the x, and then switching the x and the y, and then you can get the coordinates for the inverse. All right, properties of the logarithm function. The domain is a set of positive real numbers. The range is real numbers. The x-intercept of the graph is 1, and there is no y-intercept. The y-axis, x equals 0, is a vertical asymptote. Because remember, the exponential function, the line y equals 0 is a horizontal asymptote, so that makes the y-axis a vertical asymptote. A logarithmic function is decreasing if a is between 0 and 1, and increasing if a is greater than 1. The graph contains the point 1, 0, a comma 1, and 1 over a comma -1. The graph is smooth and continuous with no corners or gaps. All right, we're talking natural log now. So natural log is base e. So e is a very special number. It's great at modeling growth and other natural phenomenon. So we give it its own special logarithm function called the natural log. So it's y equals ln x, and it is x equals e, base e to the y. So when you see natural log, and this is a logarithmic function that your calculator will actually calculate for you. So if we are going to find the domain of the negative natural log x minus 2, the same rules apply. We need to we need this value to be, we can't take the log of a negative number. So the domain is all x values greater than 2. So that makes our vertical asymptote at 2 because it's a shift. We are reflecting across this negative, causes us to reflect across the x-axis. So we were like this, now we're like this, and then we shift over 2. Graphing a logarithmic function and its inverse. Find the inverse of f. Use the inverse to find the range and graph the inverse. So if I have, of the previous function that we have. So if we have f of x equals negative natural log x minus 2, the inverse is e to the negative x plus 2, so we do the opposite of our functions. I'm going to skip that because I find that rather valuable. Okay, so the other logarithmic function that we give its own name to is the common logarithmic function, or common log. Its base is 10, and we have y equals log base 10, and if you notice, we don't write the base when it's base 10. It's like the difference between writing x and 1x. We are implying that when there's no base written, we know it's base 10. So this guy is equal to x. X equals base 10 to the y power. So that looks like this guy. He gets really close to the x-axis. The y equals log x. Gets really close to the y-axis, swings and hits 1, 0, and then goes off in a rainbow-like manner to infinity. Okay, so if we're going to find the domain of the logarithmic function, we want to know which values we have to have our input values greater than 0. So if we have our original logarithmic function, it is going to shift right 1. So our vertical asymptote is going to shift to the right 1 and become x equals 1. It's going to be our new vertical asymptote. And it's going to have a stretch of 3. So it's going to get taller. That's exciting. So our domain, our domain is going to be, from the graph, determine the range and vertical asymptote. So the vertical asymptote is at x equals 1, and the range is from negative infinity to positive infinity. All right, we're going to find the inverse of 3 log x minus 1. So the inverse is the opposite of all these items. So when I have a horizontal shift to the right, that's going to translate itself to a vertical shift. So where it says -1 here, I'm going to put a +1 on the outside of my function. I have a log base 10, so I'm going to have my base 10 here. And here I have a vertical stretch of 3, but my inverse is going to need a horizontal compression of 1/3. So instead of timesing my function by 3, we are going to divide my exponent by 3. And that'll give us the inverse function. Use the inverse to find the range of f. And graph f. So the range of f is from, well, we can't be, y equals 1 is, so we can't be any less than, we can't be less than or equal to 1. So we have to be greater than 1. So my range is from 1 to infinity. Good times. Okay. Let's solve logarithmic equations. So if I have log base 2 of 2x plus 1 equals 3, I'm going to rewrite that as 2 to the 3 equals 2x plus 1, which is 8 equals 2x plus 1. Subtract 1 from both sides, divide by 2, and I get x equals 7/2. All right, so for b, my base is x, my exponent is 3, and that equals 343. Let's check this out. If we go, if x is equal to 7/2, so we go 2 times 7/2 plus 1, so 2 divided by 2 is 1, times 7 is 7, plus 1 is 8. Is 2 to the third power equal to 8? Yes. All right, so let's look at B. We're going to rewrite this in exponential form. So x is our base, 3 is our exponent. It is equal to 343. So something to the third power is 343. So you can do that by taking the cubed root, and you get x equals 7. I'm going to do a little check. So is 7 to the third power equal to 343? Yes, it is. All right. When we have x in the exponent, the first thing we want to do is make sure we divide, subtract, multiply, we get the base all by itself. So the first step I'm going to do here is divide by 2. And then we get e to the 3x equals 3. Then I'm going to convert it. And in this case, because I have a base e, it's going to be natural log. So natural log of 3 equals 3 times x. I'm going to divide both sides by 3. When I can put natural log into my calculator. But in order to get an exact solution, you just have to keep it in this form. You can put it in your calculator. Make sure you either put a parenthesis around natural log of 3 before you divide, or hit enter before you divide by 3, because it'll have a tendency to take the 3 divided by 3 first and then apply the natural log. So make sure you either parenthesis your numerator or press enter before you divide by 3. So the approximate solution is 0.366. All right, let's look at this word problem. Blood alcohol concentration is a measure of the amount of alcohol in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a BAC of 0.02% is 1.4 times as likely to have a car accident as an individual that has not been drinking. The relative risk of an accident with a BAC of 0.02% is 1.4. Recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by the equation of R equals E to the KX, where X is the percentage of concentration of alcohol in the bloodstream, and K is the constant. Research indicates that the relative risk of a person having an accident with a BAC of 0.02% is 1.4. Find the constant K in the equation. So we're going to plug in 1.4 for the R, for the risk. We're going to plug in 0.02 for the percent of concentration of alcohol, and we're going to solve for K. So we're going to rewrite this as a natural log function. I'm going to write natural log, because that's our log base E, of 1.4 equals 0.02K. So what we have done is we've taken the variable in the exponent and put it outside so we can do some algebra manipulation and find the answer. So we divide by 0.02. So K is equal to the natural log of 1.4 divided by 0.02, which is approximately equal to 16.82. Take a pause on this video for a moment. Do this in your calculator. Make sure you can get this calculation to work out right. It's really going to be important so that before you take an assessment, you know how your machinery operates. Okay, so part B, using the value of K, what is the relative risk if the concentration is 0.17%? So we know K is 16.82. So we're going to go R equals E to the 16.82 times 0.17, and we get 17.5. Also, again, make sure, take a pause on this video, make sure you can plug this into your calculator and get out 17.5. For a concentration of blood alcohol of 0.17%, the relative risk of the accident is about 17.5. That is, a person with a blood alcohol of 0.175% is 17.5 times as likely to have a car accident as a person with no alcohol in the bloodstream. All right. What blood alcohol concentration corresponds to a relative risk of 100. So we're going to set this equal to 100. And we're going to rewrite this as natural log. So natural log of 100 equals 16.82 divided by 16.82. And anybody with a 0.27 blood alcohol concentration has a relative risk of an accident 100 times greater than somebody without it. If the law asserts that anyone with a relative risk of 5 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI? So we're going to set R equal to 5. We're going to write it as a natural log and then divide by 16.82. So that's about a blood alcohol of 0.096. All right, so here's the summary of properties of logarithmic function, and that is our lesson for today.